Well, of course, I don't think in odds, so I want to go one step further and translate the odds into a probability. Well, here are the odds. The odds is just the probability divided by 1 minus the probability. So we can actually solve for p here. So to solve for p, for example, for this first one, I'm going to multiply both sides of my equation by 1 minus p. Then I'm going to get that p is equal to 8.33 minus 8.33p. I can add that 8.33p. I'm going to add 8.33p to both sides of the equation here. Then I'm going to get 9.33p is equal to 8.33. Now to isolate p, I'm going to divide both sides of the equation by 9.33. A general formula here is you would do p is equal to the odds divided by 1 plus the odds. And when you do that, 8.33 divided by 9.33, notice that's always going to be a number between 0 and 1. So that's going to give you a probability. That comes out to be 89%. So the predicted probability for somebody who does 0 hours per week of homework is they have an 89% chance of being book smart. Less homework, more chance of being book smart. When you do this for 10 hours per week, you get 85% is the predicted probability of being book smart. For somebody who does 50 hours per week, they're only 54% chance. Their predicted probability of being book smart is only 54%. Again, none of this is statistically significant, but just in terms of the effect sizes here, these would be the predicted probabilities. So out of a logistic regression model, you can predict for a particular person their probability, given their characteristics, of having a particular outcome. You can also say just how good of a job does the model do of predicting an outcome. You measure this with something called the area under the curve, the area under the ROC curve. And the area under the curve for logistic regression is analogous to the R squared that we got out of linear regression. It's a measure of model fit and how good your predictive power is. Remember that when we did linear regression, sometimes you could overfit your model and get really good R squareds that actually didn't mean that you had great predictive power. It just meant that you had an overfit model. Same principle applies here. Sometimes a really good area under the curve reflects overfitting rather than good predictive ability, so just kind of keep that in mind. I just want to briefly review the ROC curve. So let me give you the big picture first. So this is an ROC curve. This is the ROC curve for the model we just fit. Homework hours predicting book smart, street smart. This is actually a really bad ROC curve because homework is not very predictive of the outcome here. It's not significantly related. An ROC curve, here's the diagonal line. If you look at the diagonal line here, the diagonal line on the ROC curve means no predictive ability. So if your model falls right near this line, that means your model has no predictive ability, really. And that's essentially what's happening here. Here's our ROC curve in blue. It's not doing much better than the line. This line represents chance, that you're just flipping a coin to determine whether or not somebody has the outcome or not. So we're not doing much better than chance here. An area under the curve of 50% means no predictive ability. An area under the curve of 60%, which is what we have here, you can see that here, is really not much better than that. What is the ROC curve, though? What we're looking for on the ROC curve, you have really good predictive ability when you get a curve that looks like this, where that is an area under the curve is going to be close to 100%. The ROC curve is, what it actually is you're graphing sensitivity against 1 minus the specificity. High values, close to 100%, is really good predictive power, assuming you're not overfitting. Values close to 50% are poor or no predictive power. So that's the general picture of the ROC curve. And this, my computer, when I did the logistic regression, it spit this curve out for me automatically, so I didn't have to do any work to get it. But just to give you a little bit of detail about where it comes from, so you sort of understand that, let me show you how this ROC curve is drawn using this particular example. Again, my logistic regression model gives me out a predicted probability for every person. In this case, the predicted probability for a given person only depends on the number of hours of homework that they reported doing every week. So if you did 0 hours of homework, you were predicted an 89% predicted probability. If you did 50 hours of homework, you had a 54% predicted probability, and so on. what we can do is we can calculate the predicted probability. Again, the computer's doing this for me. That we can calculate the predicted probability for every person in the data set. And some of these will be ties because there's some people who have the same homework time and thus the same predicted probability. So I'm just showing here some of the predicted probabilities from my data set. I'm not showing all. I'm showing, I've lined up the predicted probabilities from the lowest in the data set to the highest, and I'm not showing the ones in between. I'm just showing the lowest and the highest, just to illustrate. What you then do is, again, the ROC curve is based on sensitivity and specificity. But we have a continuous predictor here. So it's not that, you know, I have a test and you either pass the test or you fail the test. To get sensitivity and specificity from a continuous predictor, we're going to have a range of sensitivities and specificities. The ROC curve is set up by doing the following. You take the person with the lowest predicted probability in your data set. You make that lowest predicted probability the cutoff for being classified, in this case, as book smart. So you say everybody who has a predicted probability of 0.52 or higher is going to be called book smart. Well, since everybody in your data set has a predicted probability of 0.52 or higher, everybody in your data set is going to be classified as book smart. So we can actually make a little 2x2 table here. If our test is, if your predicted probability is greater than 0.52, greater than or equal to 0.52, you're going to be classified as book smart. That is a positive test. Then all 48, there's 48 people here, all 48 are going to be classified as book smart. You're classified as street smart if you're below 0.52 on this particular cutoff. That means nobody will be classified as street smart to start here. And this is there, we can actually then compare that to the true value for book smart or street smart. So in my data set, out of 48, there were 40 book smart people and 8 street smart people. If we count them all as book smart according to our test, then we are going to have perfect sensitivity and 0 specificity. So we've captured everybody who is book smart. If you make the test predicted probability 0.52 or higher, we're going to capture everybody who's book smart, but we're going to capture nobody who's street smart. We're going to misclassify all of them, so our specificity is going to be 0. We represent that on the ROC curve right here. So this is 100% sensitivity and 0% specificity, because remember we're graphing 1 minus 0, 1 minus the specificity. So 1 minus 0 gives us a 1.0 value here. So we end up here on the curve. Then we do this again. Now we move up our cutoff for classifying people as book smart or street smart to the next predicted probability level, which is 0.54. So now we say everybody who's 0.54 or higher on their predicted probability, we're going to call you book smart. And in fact, when we do this, that is going to capture most, everybody has 0.54 or higher, but not everybody. So that's our positive test. Our negative test, now there are a few who are below 0.54. They're going to be counted as having a negative on this test. So we end up with classifying 46 people as book smart according to our test, but 2 we're classifying as street smart according to our test. We can actually look at the true value, who was actually book smart and who was street smart. We had 40 in our set who considered themselves book smart. And in fact, we ended up with 38 out of the 40 who were book smart were correctly classified as book smart, and 2 were misclassified. The 2 who had predicted probabilities less than 0.54 were actually out of the book smart group. And we misclassified the 8 street smart people as book smart again. So our specificity remains at 0. Our sensitivity is now 38 out of 40, or 95%. So we no longer have perfect sensitivity. That's going to move us down on the chart here to a sensitivity of 95%, and we're continuing to have a specificity of 0. And we go on and do this for all the predicted probabilities in our data set, and that's what defines this curve here. And again, if we have no predictive ability, you're going to end up right along that line as we do here. So that's the ROC curve that tells us how predictive our model is. The other thing that's often more useful or more commonly used from the logistic regression model is just to say what's the relationship between the predictor and the outcome, in this case homework and book smart. And as I mentioned earlier, the beta coefficient from logistic regression, what happens is if you exponentiate that beta coefficient from logistic regression, when you exponentiate that, that gives you an odds ratio. So we can take this beta for homework here, and we can exponentiate it, and so we can raise that to negative 0.0389. When you do that, you come out with a value of 0.96. So that's the odds ratio here. I'll show you in a minute why you can interpret the beta like this. But what this means is we have quantified the relationship between homework time and your odds of being book smart. And you would read this odds ratio of 0.96 to say that there is a 4% decrease in your odds of being book smart for every 1 hour more that you spend on homework per week. So if I just exponentiate that beta, the units here are in 1 hour of homework per week. Notice now we've got an odds ratio for a continuous predictor. You can get that out of logistic regression. So now we're talking about the increase in odds for a 1 unit increase in the continuous predictor. Everything up to now when we've done odds ratios, we've been talking about a binary predictor. You're either in this group or you're not. But now we can get odds ratios for continuous predictors. Well, how does that translate? How does that beta become an odds ratio? Exactly how does that work? So let me show you that now. How do we get from beta to odds ratios? Well, what is an odds ratio? If I want to know the odds ratio for being book smart for the exposure here, which is more homework time compared to less homework time, what is the odds ratio? An odds ratio is a ratio of 2 odds. So my odds ratio here would be the odds of being book smart for somebody who does more homework compared with the odds of being book smart for somebody who spends less time on homework. And if we're just going with the units that I've used here, the difference between the numerator and the denominator, I could make it a 1 hour difference in homework time. So what's my odds ratio for a 1 hour change, a 1 hour increase in homework time? How does that affect my odds of being book smart? Well, now I can just fill in. I fit a model that tells me that predicted odds of being book smart for a given homework level. So I can just plug in that model. So what's the odds of being book smart for somebody who does, say, 1 hour of homework compared with somebody who does 0 hours of homework? The odds, which I can put in the numerator, so I fit the model that says the log odds is alpha plus beta homework times the amount of homework. If I exponentiate that, remember, I get the odds. So the odds of being book smart for somebody who does 1 hour of homework, I can put that in the numerator. I can compare that to the odds of being book smart for somebody who does no homework. So now I've made a ratio of 2 odds. The odds for somebody who does 1 hour of homework divided by the odds for somebody who does no homework. And then we can simplify this a little bit. What you'll notice right away is you have to know a little bit about how exponentials work to know how I leapt from here to here. But if you have e raised to alpha plus beta, that's the same as e raised to alpha times e raised to beta. Well, notice there, they both have the same intercept, so those intercepts are going to cancel. That's the nice thing here. Those cancel, and if we simplify this, it just turns out that we're left with, if e beta times 1 in the numerator divided by e raised to 0 in the denominator, that's just e raised to beta homework. And so that's the odds ratio. You take the beta for homework, you exponentiate it, you get the odds ratio. In the actual value here for the beta was negative 0.039. Again, if I exponentiate that, I get an odds ratio of 0.96. So the odds ratio of 0.96 means that for every 1 hour increase in homework per week, your odds of believing yourself book smart decreases by 4%. Of course, it wasn't significant here. I want to just extend this logic to show how not only can we get odds ratios out of logistic regression, we can get multivariate adjusted odds ratios. So just as we made the leap from linear regression, simple linear regression, to multivariate linear regression, we can do the same thing with logistic regression. It's very easy to add additional predictors to the right side of the equation. We can have a bunch of predictors just like this. That's our multivariate logistic regression equation. And here's some examples. Imagine that we did a study where we were looking at lung cancer. And let's say for the first logistic regression model we fit, we put in as predictors a binary predictor for smoking and a binary predictor for drinking. So we looked at smoking, yes or no, and drinking, yes or no. Those are 2 binary variables. So that's one model we could fit. That's a simpler model, so I'm going to start there. The beta for smoking would then represent the effect of smoking adjusted for drinking. The beta for drinking represents the effect of drinking adjusted for smoking. we can make it slightly more complicated by also adding an additional variable, additional predictor in the model. Let's add also age. We could then get the effect of smoking adjusted for both drinking and age, the effect of drinking adjusted for both smoking and age, and the effect of age adjusted for both smoking and drinking. Let me show you now exactly what I mean by adjusted for. When I keep using that term adjusted for, what does that really mean? That means that if I fix everything else in the model, it's the isolated effect of smoking or the isolated effect of drinking. So let me show you that mathematically now. I think it's helpful. I'm going to start with the binary predictor, the model with the two binary predictors because it's simpler. Again, what's an odds ratio? It's the odds of a disease, say lung cancer, for an exposed group compared with the odds of disease for an unexposed group. If I have just a binary predictor, say exposed and unexposed, drinker and non-drinker, smoker and non-smoker, that's what an odds ratio is. My logistic regression model models the odds of disease for given people. So I can put in the numerator the odds of disease for, say, a drinker, and I could put in the denominator the odds of disease, lung cancer here, for a non-drinker. And that's what I've done here. So my model, my first model, had alcohol and smoking, two binary predictors in it. So if I want to know the odds ratio for drinking, adjusted for smoking, I can just say, let me compare in the numerator the odds for a drinker, and in the denominator the odds for a non-drinker. So there I put in a 1 for drinking and in the numerator and a 0 for drinking in the denominator. Now I'm comparing the odds of lung cancer for a drinker compared with the odds of lung cancer for a non-drinker. Now I've also got smoking in the model, so I have to put in something for smoking, but what if I hold it fixed? So what if I say I'm only comparing a drinking smoker to a non-drinking smoker? So I put in a 1 for smoking for both the numerator and the denominator. I hold smoking fixed. It actually wouldn't matter if I chose to compare a drinking non-smoker to a drinking non-smoker. I just have to hold smoking fixed for both the numerator and the denominator. I have to make it the same. If I make it the same, what you can show is, again, the intercepts cancel, and now, as long as I hold smoking fixed, the smoking betas cancel. What am I left with? Well, if I simplify this, I just have e raised to beta alcohol. E raised to 0 in the denominator is 1. So I can show that the odds ratio for drinking, if I hold smoking fixed, is all I do is take the beta for alcohol and exponentiate it. That gives me the odds ratio for lung cancer for a drinker compared to a non-drinker, and again, where I've held smoking constant. Notice that this will be the odds ratio for drinking if I compare two smokers or if I compare two non-smokers. So I'm assuming that the effect of drinking is the same in smokers and non-smokers. I can use the same logic to show you that this works for a continuous predictor as well. So here's a continuous predictor. For a continuous predictor, I'm going to be comparing, again, the odds of disease for somebody with a higher level of the continuous predictor compared to somebody with the lower level. For example, imagine that I've got my second model here that's got alcohol, smoking, and age in the model. Age is a continuous predictor. If I want to compare in the numerator an older person, the odds of lung cancer for an older person compared with the odds of smoking for a younger person in the denominator. This will give me the odds ratio for an increase in age. How much does age affect my odds of lung cancer? I'm again going to hold all the other variables in the model here, alcohol and smoking. I'm going to hold those fixed. So say I have two drinking smokers, and I'm comparing a drinking smoker who's 29 years old to a drinking smoker who's only 19 years old. That's a 10-unit jump in age. And you'll see it wouldn't really matter if I had put in 40 and 30 or 50 and 40. Any 10-unit jump in age is going to give me the same answer here. You'll notice that lots of things cancel out. That's the great thing here. So we fix all the other variables, they all cancel out. So we're left with that the beta for age, in this case, if we, and if you solve it here, beta e raised to beta 20 times 29 minus e raised to beta 19, that's the same as e raised to beta age times 10. So what this tells us is that if I multiply the beta for age times 10 and then exponentiate, I will get the odds ratio for a 10-unit jump in age. So this would give me, for a 10-unit jump in age, a decade increase in age, what's the increase in my odds of getting lung cancer? If I wanted to do it for a 1-unit increase in age, I would just take the beta for age and exponentiate it directly. That would give me the odds ratio for a 1-unit increase in age. It doesn't really matter what you pick for the units of age, but you want to pick something that's sort of meaningful. A 1-unit or 10-unit increase is probably reasonable. that gives you the odds ratio for that unit jump. You can see that for a continuous predictor, the magnitude of the odds ratio will depend on the units. It's not going to, what units you choose will not affect the p-value, but it will affect how big or small that odds ratio looks. Just keep that in mind. You always have to give the units in your table so people know how to interpret that. This is the odds ratio for age, adjusted for smoking and alcohol, which means that we've held smoking and alcohol fixed. So that is, if we're looking at two people who have the same level of smoking and alcohol, and the only difference between them is a 10-unit difference in age, this would be the effect of that age. So just to summarize, the practical interpretation here is if you take the beta, the slope from a logistic regression for any of your exposures, your predictors, and you exponentiate it, you get the odds ratio for that exposure. And you would interpret that as this is the increase in the odds of your outcome for every 1 unit increase in the exposure, adjusted for, controlling for all the other variables, all the other predictors that are in the model. And we'll practice looking at an example of how to use this in the next module. Just to tell you, most computer packages, when you run a logistic regression, you don't actually have to even do the exponentiation. Most computer packages will automatically give you the odds ratio. So again, out of a logistic regression, we get these multivariate adjusted odds ratios.